Hello, my name is Aneta. I'm a PhD student at the Ludwig Maximilian University in Munich, and today I will present a joint work with my supervisors Martin Ringsquandl from Siemens and Professor Volker Tresp from the Ludwig Maximilian University, titled Adversarial Attacks on Tables with Entity Swap. For more details on this work, you can also check out the paper that can be found on the official website of the Tabular Data Analysis Workshop. The task of solving the table interpretation problem consists of several subtasks, including the column type annotation, where a column is annotated with a semantic type, entity linking, where a row or a cell from a table is linked to an existing entity, and a relation extraction, where a link between two columns is extracted and linked to an existing relation. In this paper, we are focusing on the problem of column type annotation, where a column is annotated with a semantic type. This problem is commonly solved under the open book scenario, meaning that we have access to online available knowledge graph that contains information about entities and their semantic types. And then using a lookup-based service, the first step would be to search for entities from the specific column using the lookup service and then retrieve candidates that can be linked to the entities from this column. Then the column would be annotated with the semantic type that takes the majority vote among the retrieved entities. However, if we look into tables with novel entities, this approach with the Wikidata lookup service would fail because newly entities that still haven't been added to the Wikidata graph would not return any candidates, and therefore the lookup would fail. However, it is still possible, in some cases, it's still possible to classify columns using the table context. Another approach for solving the CTA problem is under the closed book scenario when there is no access to available knowledge graph. Instead, provided that there is enough label data for a training set, including labels for columns in the training tables, a classification model H is trained to correctly predict the class Y for the input column J from table T. Then, during inference, the classification model is evaluated on a test set, which includes tables that have not been seen previously, and then the model should infer the class of a column in the unseen table based on the knowledge that it gained during the training phase. However, having a close look into the training and test sets commonly used for evaluation of the column type annotation problem, we can see that there is an existing overlap of entities between these two datasets, and it's a significant overlap. Namely, in the table here on the right, we can see that this overlap can be up to 80% of the entities. So this means that 80% of the entities from the test set has also been seen also during the training of the model. This raises a question about the performance that the machine learning models used for solving this problem are usually used, because it is a question how well they can generalize or how well they have overfit on the entities that they have seen during the training set. And this is our main motivation for the adversarial attack that we are presenting today. So adversarial attacks have a rich background in the image domain, where we know that adding just a slight noise that is imperceptible to human to an existing data set, that the prediction made by the previously good classifier can be changed with a quite significant confidence. Now, adversarial attacks for tabular large language models have not been explored so far, and therefore in this work we explore what would be the appropriate noise to introduce to a table so that the column type annotation classification model would misclassify a column. In this direction, we propose a tabular entity swap. So with the entity swap CTA attack, we aim to find the key entities for each column and then to gradually select these entities and swap them with adversarial examples. So As we mentioned, the output from the classification model for a column is the logit vector OY, and we calculate the importance score for every entity in a column as the difference between the logit output of the model when the entity is in the column, as it is in the first case here, minus the logit output or y minus the first entity. So this will give us the score, the importance score for the first entity in this column. We calculate this importance score for all the entities in a column, and when choosing entities to swap in a targeted column, we always choose based on their importance scores and substitute them with adversarial entities. By sorting the entities according to their scores, we ensure that the attack consistently targets the key entities within the specific column. Once we have selected the key entities for swapping with adversarial ones, the next step is to find the most different entity that is of the same type as an adversarial example. So in order to adhere to the assumption that the attack is imperceptible for humans, we always constrain the search space for adversarial entities to include only entities belonging to the same class. As I mentioned, there is a substantial overlap of entities between the train and test sets that are used for evaluation of this task. Therefore, we propose two different sampling sets from where we take adversarial examples. The first one contains all the entities per class that appear in the test set. And then the second set contains only novel entities, that is entities that appear only in the test set. The entities that have been seen during training have been removed from this set. We refer to this set as the filtered set, and here it's shown with red. Now, for sampling adversarial examples from these sets, we proposed a similarity-based strategy where we compare the contextualized representation for both the original entity and all the entities of the same class, and then we take the most dissimilar entity as the adversarial example. Another strategy is also to choose an adversarial example at random. So in this example here, we can see that when choosing at random, we can choose Nikola Jokic as a substitution for Rafael Nadal in the targeted column. But if we take the most dissimilar entity, then we would substitute Rafael Nadal with the entity Olga Karmana. And then the goal of our attack is that the CTA model would misclassify this column. To evaluate the effect of the proposed adversarial attack, we conduct experiments attacking the thorough framework for table interpretation, specifically on the column type annotation task. This plot shows the achieved results of the evasion attack on the thorough framework. With the red line, we show the performance reported by the thorough paper on the CTA task of 0.88 F1 score. Every dot here shows the drop of the performance that the model achieved on the attack dataset. So in the evaluation, we gradually increase the percentage of entities that we swap in the columns, ranging from 20 to 100%. And then for choosing the adversarial entities, we sampled from the filtered space, which includes only novel entities, or from the test set, where we also have overlap with training. And then for sampling the examples, we sample them at random or using the similarity-based strategy. Here we can see that using the similarity-based strategy and sampling from the filtered set induces a significant drop in performance of the model. So the drop is 6% when replacing 20% of the entities, but it goes up to 70% drop when replacing all of the entities in the column. In conclusion, we showed in this work that the entity leakage is a major weakness in the current setup of the column type annotation problem. We presented the first adversarial attack on tabular language models by exploiting this weakness in the test dataset, and our results show that the simple entity swap attack is already effective. Now, as a future work, there is lots of room for improvement of the proposed adversarial attack. For example, we can choose time-evolving novel entities, or we can also use the popular generative models to sample plausible fake tables that can also trick the model. Thank you for your attention.